Welcome back to our Chem 152 video series. In this video, we'll talk about how to use Hess's law to find change in entropy. In this question, our task is to find the standard entropy change for a reaction, but rather than being given a reference table of standard entropy values, we are given the entropy values of other equations. Our first task is going to be to look at every item in the reaction and locate it in the system of equations. If we look to nitrogen gas, we notice nitrogen gas is located in the second line on the right side. We'll make a note of that here. We also note that oxygen gas is located in line 3, also on the right. And we note that NO gas is located on line 1, also on the right side. So now that we know where each of our items exists in the equation, we need to check two things. We need to check to see if that item is in the correct position and if there are the correct number. If they're not in the right position, what we're going to do is reverse the reaction and multiply the entropy by -1. If there are the wrong number, we will multiply the reaction by some number to make them the right number. Not only will we multiply the reaction, we'll multiply the entropy as well. Let's begin with our nitrogen gas. In our target equation, nitrogen gas is on the left, but notice that in the system, it's on the right. So that means that this nitrogen in the system is in the wrong position. It's written on the right in the system, but we want it to be on the left. Also notice that in the system, the nitrogen gas has a 2 in front of it, but in our target equation, we only want a 1. The way we change a 2 into a 1 is by multiplying the entire line by 1/2. Therefore, we will not only be reversing this equation, we'll be multiplying everything by 1/2 and multiplying the entropy by -1/2. So when we write out our old equation in line 2, it was N2 yields 2N gas. The change in entropy was 115 joules per Kelvin. But our new line 2, we'll write the equation backwards, saying 2N gas yields N2 gas, which would change our delta S standard to -115 joules per Kelvin. But also, we're going to multiply everything by 1/2. As I said before, this includes the entropy value. Therefore, our new line 2 will now be 1/2 times 2, which is 1 nitrogen gas, yields 1/2 N2 gas, and our delta S standard will become -57.5 joules per Kelvin. Now let's examine the next item in our target equation, which was oxygen gas. If we look at our target equation, oxygen gas is on the left, but in the system of equations below, we see oxygen gas is on the right. And this means oxygen gas is out of position. To fix that, we will reverse the third line, and then we will change the entropy to negative. But also notice that we have the wrong number of oxygens, because in the system we have a 2, but in the target we need a 1. In order to change the 2 to a 1, once again, we will multiply the equation by 1/2 and multiply the entropy by 1/2. Let's do those operations. We'll begin with our old line 3, which is O2 gas, yields 2O gas, with an entropy of 117 joules per Kelvin. We have to now reverse the third line to fix the positional problem. So we'll have 2O gas yields O2 gas. And our delta S will change to negative 117 rather than positive 117. Now we multiply that line by 1/2 and also multiply the entropy by 1/2. If we do this, we will get 1 oxygen gas, which is what we want, yields 1/2 O2 gas, and the entropy value will change to 58.5 joules per Kelvin. We'll include that it's also negative still. And we'll copy down that third line and write it underneath our new second line. Now let's examine the third item in our target equation, NO gas. We noted that NO gas is in line 1 on the right side. That agrees with our target equation because in our target equation, NO is on the right. So there's no need to reverse this time. However, when we look at the number of NOs, there's a mismatch. We need 1 NO, but we have 2 in the system. So to fix that problem, again, we're going to multiply by 1/2 to change the 2 NOs to 1 NO. Let's write down our old line 1, which is N2 plus O2, yields 2 NO with an entropy value of 24.8 joules per Kelvin. Now we're going to multiply everything by 1/2, including the entropy. So our new equation is 1/2 N2 gas plus 1/2 O2 gas yields 1 NO gas, and our entropy value will change to positive 12.4 joules per Kelvin. We'll write that above our new line 2 and line 3 here in our new system. Now that we've collected our new entropy values, all that's left to do is try to simplify this system down. Now that we have our new system assembled, we can begin trying to cancel out our reactants and our products. When you cancel out reactants and product, you're looking for something that's identical on both the left and right side of the system. To help us visualize this, we'll draw a red line through the arrows. Anything on the left side of that red line is a reactant. Anything on the right side is a product. And we might notice on the left side we have 1/2 N2 gas. And on the right side we also have 1/2 N2 gas, and this means we can cancel those out. We might notice also on the left side we have 1/2 O2 gas, and on the right side we have the same. Those can cancel out as well. If we look at what remains, on the left side, left over, we have N gas plus O gas yields, on the right side, just NO gas. This matches our target equation, and we've verified that we've done our math correctly. Now all that's left to do is the arithmetic to add together all of these entropies. So we'll take 12.4 minus 57.5 minus 58.5. We get negative 103.6 joules per Kelvin for our entropy. Notice that in our target on the left side we have 2 moles of gas, and on the right we have 1 mole of gas. Therefore, our moles of gas have gone down, which matches up with the answer we've got, because we expect when our moles of gas goes down, our entropy change should be negative. And this is a good way to verify that you've done your work correctly. Thank you for watching, and we'll see you again soon.